Hey, hey, can you say something?
Yes, I can hear you.
Okay, good. Because I had uh these earphones here were ringing in my phone about a minute ago, and I've had a bad luck with that in the past with the phone ringing and then all of a sudden it taking over, sort of like the speaker for the moment. So can you say one more time that you're here?
Yeah, I'm here.
Good. Happy, happy. Okay, so right before class started, like I said, I got that phone call and I feel now a little discombobulated. But what I want to do is to sort of start with sharing a screen, unless you have a question while I'm in the process of doing that screen sharing.
No, I'm pretty good so far.
Okay. So, I guess we're at a good place, other than you all have exams that you should be finishing up. It's not due today. It's due by Friday, 11:59 p.m. So let's just say 36 hours, about a little bit less than 36 hours from now, you should have turned in the test, and things should be good with it. Let me know, of course, if there's any unexpected things, any surprising things that happen during the course of working on the test. Canvas has done a good job with solving a lot of the problems that were there back in the early part of COVID. The 2020 Canvas, things are a little bit better now, especially with regard to testing, but still, internet outages just always a thing. And so if you bump into a problem with that, be sure to let me know ASAP. Don't panic, don't worry about it. I can always open the test again later for you. It's just it will require a little bit of a technology dance, if you will. Okay, so maybe starting with things related to administrative announcements. One of them is you all have seen me send out the announcement and then send out the revision of the announcement that office hours today, the earlier time slot coming up in a couple hours, 3:25 to 3:50 is when office hours will be. Normally on Thursdays, it's following my afternoon class, so it would be 5:10 to 5:35, but instead it's going to be 3:25 to 3:50 today, right before that later class. If you got any questions, definitely show up there. Or oddly enough, send me an email because I can reply to emails, even if I'm only with my phone and I'm working on that and that alone. To especially if you sort of give me in the email like a context for the question, like, oh, on this problem in the book, or on that problem on the homework assignment about the partial F test, could you please explain why? Just do a little screenshot to remind me of what is going on and maybe what the answers were that I posted. And then even with the phone, I can sort of hit a quick reply and get you what you need earlier rather than later. What else? So yeah, work on the test. The lab activity for the day in chapter 10 is completely unrelated to content on our exam. The exam goes up through chapter 9. 8 and 9 are sort of covered, I guess, in a technical sense on the exam. But, I'm sort of thinking that that mostly it's not material in chapter 9. Okay. Chapter 8 and 9, not really much of the test, but still, just in case, you won't have been harmed by doing the chapter 8 and 9 homework problems before today. And I think the answers to those chapter 8 and 9 homework problems, as well as the answers to the partial F test and interaction follow-up questions, those are already due last night at midnight. And so I would recommend looking over the answers to those problems before taking the exam. Look it over, make sure you have no questions. And if you do, let me know before taking the exam. Okay, so that's all of the administrative things I wanted to be sure to mention to you all. Do any of you have a question related to anything administrative at all before we pick up and move forward into chapter 10?
Yeah, just to confirm, the midterm is chapters 5 through 9?
4, 5, 6,
Four? Okay.
7, 8, 9, with not as much emphasis on 8 and 9.
Okay,
So,
good to know.
yeah, you'll probably see a question that you'll think, oh, yeah, yeah, chapter, that's sort of a chapter 9 question. But you could also look back and say, but we learned that way back when we talked about regression, or we learned that way back when we talked about analysis of variance. And so, chapter 8 and 9 are sort of a good place to end on in the material that's covered. It's because it's stuff we've done before. So yeah, basically, I think chapter 4 through the partial F test is the area of emphasis, and students find chapter 7, the interactions, the most challenging. And so, if you have, before we move forward, let's sort of talk about any questions you might have from the sample exam or general concepts, and especially interactions of the partial F test are great things to raise as issues right now before we move into chapter 10. But that's only if you want.
Yeah, I think I'm okay. We can probably move on.
Cool. Excellent. So then let's sort of slide forward a little bit into at least what's going on this week. Um, and I think, darn it, I think I need to, where it says review design two. Okay, yeah, I guess that's a valid description of that. Literally in chapter 10, I've entitled it in a lot of places quantitative categorical variables or quantitative factors. But if you look here at the sort of title for this part of the week, it says design part two. Yeah, our chapter 5, where it says design of experiments in chapter 5. Um, that's like right here, week 3, part A. We're literally sort of picking up that context, a set of concepts, and moving forward in that section. And the real key thing is sometimes in experiments we have numbers that are the levels that we use for a categorical factor. Okay. And an example that I think I've used in this class before, but I might have lost the data set. But there was a grad student in I guess fruit science. I guess not really fruit science, but what was it? Crops. Okay, sort of in ag in general, but in crops in particular. And he was someone who worked at a vineyard, and they're producing Pinot Noir, Pinot. And what we're going to do is drop fruit, if you will, in the springtime. You see, oh, look, there's a whole bunch of clusters on this grapevine. And you'd say, that's too many clusters on the grapevine. The biology says we're going to put a lot of energy into producing, these lots and lots of grapes. Wouldn't it be better if we had that same amount of energy but pushed into fewer bunches of grapes? Okay, we might have better quality grapes, if you will. That's the idea. And so you could very well say to your crew, say, okay, go out and drop some of the fruit until there's exactly 4 tons of grapes per acre. Now that's hard to get exactly right, but usually the foreman on the group says, okay, make sure each plant has about 20 clusters. Okay. Or you could say, make sure each plant has about 15 clusters, which will map to about 3 tons per acre, or only 10 clusters of grapes per vine, which will be, 2 tons per acre, or maybe it's going to be only 1 ton per acre if you get 5 clusters of grapes per vine. I'm in the number, but you selectively prune, get rid of some of the grapes during the growing season. Okay. And we could fit in ANOVA, and we could say, is there any difference in the average between 1 ton per acre, or 2 or 3 or 4 tons per acre? We could say that we really want to know, is there a difference across those different tons per acre? Is there an effect of tons per acre? and and the effects, those alpha hats, if you will. Okay. The way we're going to sort of model that with ANOVA is basically saying across our categories, is there any difference in the means? Or if we have other variables entered into our analysis, um, we would say, are there effects, noticeable estimated effects of one, two, three, or four tens breaker? But one, two, three, and four, they're numbers. Couldn't it just fit a trend line? And if I do fit a trend line, isn't that in some ways better? What if the trend is even not linear, but curved? Oh, well, we know how to fit quadratics. So why don't we go down that path and we'll see what we could do with a data set. Now, the one that I think I wanted to use, I might be forgetting, but let's, uh, I think, okay, veg height tramping. So this is an experiment that was done at the University of Minnesota, the St. Paul campus. And uh, this guy recruited students to walk across a field of weeds. Okay. And one of the treatment levels was you walk on the weeds, not at all. 0 times do we walk across the field. Okay. And that happens one, two, three, four situations. Okay. And we just measure how tall in centimeters the vegetation gets. Okay. In each of those four treatments. And then in other fields, other locations, we ask someone to walk 25 times back and forth across this little path. And then we measure on the path that the individual walked on the height of the weeds, the height of the vegetation. Another pathway, we ask people to walk 75 times. So back and forth 75 times. That takes a little while, but we measure the height of the vegetation. And shoot, one of these, it was like 200 back and forth, and one was even 500 back and forth. So this trend, I categorical, okay? Vegetation height could be corresponding to the categorical number of tramping passes, okay? So let's go ahead and analyze that the way you would do with the ANOVA thinking process, okay? Vegetation height. Let's try just across the different treatments. Click OK. We see treatment 1, 2, 3, 4, 5. We see different means shown. In fact, I could even turn on the analysis of variance, means in ANOVA. And we see the average in each of the different groups. We do see this decrease. Okay. I could do it also with, instead of which treatment number was it, like treatment 5 goes to 500 tramping passes, I could do the same thing under analyze, fit Y by X. Okay. I could have tramping passes. Okay. And veg height depends on the number of tramping passes. And sure as heck, it looks identical to our earlier graph. Other than now we're labeling, instead of treatment 1, 2, 3, 4, 5, we're saying how many tramping passes are there? 0, 25, 75, 200, or 500. And it looks as though, one treatment level 1 or 0 tramping passes has the highest veg height. 2 and 3 look about the same on average. 2 and 3, 25 and 75 tramping passes here look about the same on average. If we go up to treatment level 4 or 200 tramping passes, it seems a little bit lower. And then treatment level 5 or 500 tramping passes, yet again, lower. So I could sort of model it with just what treatment number is it, or I could say, let's just treat the number of tramping passes as a categorical variable, and we have a trend. And I'm saying trend, but I didn't fit a trend. What if we had treated this tramping passes instead as continuous, as a number, if you will? The little blue triangle thing inside JMP says treat it like a number. And X, that would be like a regression. Okay. If I were to fit an analysis here, and let's go with fit Y by X, click tramping passes as X and veg height as Y. I'm going to fit a trend line if I were to add in, boom. I'm going to fit a trend line, and that trend line is clearly not producing results that are as good as these. R squared was 89%. Now it's like only 52% if I fit a trend line. And it looks like it's higher and then goes down and then levels out. I'm thinking maybe quadratic. Hey, could I fit this as a quadratic? So instead of fitting it as linear, why don't we fit a polynomial, a second order polynomial, a quadratic? Would that be even better? It seems like it fits pretty darn well. Let's get rid of the linear fit and focus on the quadratic fit. R squared's like much better now, 71%. And it seems as though we're doing a better job. Well, why limit ourselves to just quadratic? Couldn't we go for cubic? Under fit polynomial, it says, let's try a cubic. No problem. Well, that clearly looks a little goofy, but if we were fitting this cubic, I'm seeing R squared is even higher. Okay. And why stop with cubic? Why not fit a fourth order polynomial? Okay, let's fit a polynomial of order 4, a quartic. So x, the number of tramping passes, x squared, x cubed, x to the fourth power. We fit in that one, and clearly you're saying this red wiggly line is, or not red, this brownish color wiggly line. Maybe let's go ahead and remove it. Boom. And let's remove the quadratic. This brownish wiggly line is yeah, explaining a lot of the variability. Okay. And let's remove the linear as well, because why not? We clearly don't love that one. But this model that we fit, okay, it seems as though it makes in some ways not so much sense because it's got this wiggle and it stretches down into the negative veg height range. So, with a 400 tramping passes, you'd say you'd expect negative vegetation height. That's clearly not going to make sense. Okay. But what I'm spotting here is interesting with this fourth order model. Literally, although the picture doesn't work for me, and this trend line drawn in looks unnecessarily or unreasonably complex, the R squared value 0.887163, 0.887163, it's surprisingly the same. And in my, not just my summary fit, but my analysis of variance, look, it's 4 degrees of freedom for the 5 different levels of my categorical variable. And we have 15 degrees of freedom for error. My F ratio for my model is, to tackle the question, is any one of the levels different from any of the other levels? My F ratio is like, heck yeah, 29.4837. My F ratio for my quartic polynomial fit is 29.4837, 4 degrees of freedom, 4 degrees of freedom, 15 for error, 15 for error. This analysis of variance for this polynomial, fourth order polynomial fit is exactly the same as this one. And that really weirds me out. Let's talk about why that is so trippy. Literally, we're telling you a fourth order polynomial, a quartic model, is the exact same thing as 5 different categories. The fit is the same. And something we said 1 or 2 class sessions back was if you got 2 models and their F ratio is the same, and the degrees of freedom for the model is the same, and your R squared is the same, and your mean square error is the same, if everything is the same in your summaries, that would suggest that those models are the same model. So let's talk about why that's the case. I'm going to remember back to high school. And in high school, one of the things I learned is if you've got an X and a Y, so Y here is X there. If you have for 2 distinct X values, maybe a low one and a higher value, there's a corresponding Y. Okay. Uh, I could fit a trend line that's straight that goes through both of them. So yeah, literally 2 points determine the equation of a line. And most people in this class are like, cool, cool, I'm good. 2 points, get me a straight line. And you remember back from high school, yeah, I could do that. I could probably relearn now how to figure out the y's that correspond with that or what the slope is. But the claim is now if there's a mu for the low group and a mu for the high group, which we're estimating with the average X bar for the or Y bar for the low group. Okay, so Y bar for the low group and Y bar for the high group. Okay. Um, if I draw a trend line through the X value and the average Y, and then the higher X value and its average Y, that trend line will fit exactly the same as the two-level ANOVA, if you will, a t-test. So far you're thinking 2 points to determine a line. Got it. Happy. I remember also back to high school, if you give me three distinct X values, like that one, and that one, so there's X low, X the middling one, and X the high value. If you have a corresponding average for the Y for the low group, okay, and average for Y for the Y bar for the middling group, and then average Y bar for the high group, okay, right there, you could literally say, I've got these one, two, three separate means. I could do ANOVA, and are these one, two, three means far enough apart from each other that we're convinced that there is a real difference in the average Y across these three distinct X's? But the claim now is, oh, we had 2 points and that determines the equation of a line. Well, I've got 3 points and that will determine the exact equation of a, no, 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 no. Let's go with a different color. Okay, come on, go back. Okay, so I went back too far. Okay, let's go with black and I have, um, okay, so let's just go to a different color. I'm trying to draw a parabola here, and the parabola that I'm drawing in. Okay, I did a very poor job drawing a parabola. I apologize for that. I attempted to draw a perfect parabola that goes through those 3 points. The claim, again, 2 points to determine a line, 3 points that are all distinctly different in terms of their x value will determine the equation of a parabola. Literally, there is a relationship out there where I'd say y hat is beta 0 plus beta 1. Actually, let's go beta 0 hat plus beta 1 hat times x plus beta 2 hat times x squared. Yeah, literally, there is a intercept, a slope for x, and a slope of x squared that will perfectly go through the exact same y bar values that we had when we had fit 1, 2, 3 groups. Okay, so that's y bar for the high group. There we go. Okay, so 1, 2, 2, 3 levels for x. We've got two separate terms, x and x squared. My claim goes further. If I've got 1, 2, 3, 4 separate x levels, okay, so let's call them x1, x2, let's go with x3 and x4. And it doesn't really matter that the spacing of them, just that they're at 1, 2, 3, 4 separate locations. And I'm going to go with that as my collection of x or y's. So there's the corresponding y's. Okay. And there is a cubic, okay, relationship where y hat, nope, go with a different color. Y hat is beta 0 hat plus beta 1 hat times x plus beta 2 hat times x squared plus beta 3 hat times x cubed. That is my cubic trend line, and it will go through all 1, 2, 3, 4 values, give me the exact same fit as if I had tell with these x's as though they're quadratic. Okay, so I'm going to try and get this cubic. It does this sort of a thing. There we go. There we go. Yeah. Okay, so let's ignore the one little mistake that I made and let's move forward. Okay, so my claim is four distinct x values, three order polynomial. X1, X2, and X3. X1, X squared, and X cubed is going to have me the exact same fit. Okay, so yes, let's get back to it. Yeah, literally, we can fit a polynomial trend and it will do as good as as good as the categorical fit. Okay. So yeah, literally, if you have k different levels, and so in our experiment where the zero tramping passes, there's 25, 75, 200, and 500, five different levels. Okay. I should be able to deal with a fourth order polynomial and get an identical fit. So let's go ahead and verify the fourth order polynomial will give me the identical fit. I think we did that earlier, but let's do it now with fit model. Get rid of those. Oh, no, let's do them this way. Okay, so again, with the original data, and let's analyze fit model by veg height as a function of which treatment group it is. Click run. That's just 1, 2, 3, 4, 5 treatment effects. And focusing in on R squared, okay, the analysis of variance and your parameter estimates. There's the average veg height. The effect of it being treatment 1 is to increase the number of the veg height by 6.2. 2, 3, 4. Oh, and there's treatment level 5's effect, which is obscured from us because we only show you the first 4 of the 5. If you want the 5th, you could turn on estimates expanded to get all 5 treatment effects. Yeah, we usually just leave that off. Okay. If we had fit the model instead that was a polynomial of the 4th order, again, fit model is the way to go. Veg height right there. And my tramping passes variable, I want to use a macro, and I'm going to say a polynomial to a degree of 4. I claim the 4th order polynomial, the quartic model, is going to fit exactly the same. So highlight tramping passes, say 4th order, and under macro say polynomial to the 4th degree. It gives me tramping passes squared, tramping passes cubed, and tramping passes to the 4th power. It's hard to really see that, but you could expand it out and verify that indeed it's tramping passes times tramping passes times tramping passes times tramping passes. Tramping passes to the 4th power. Now here's where I think centering polynomials is sort of good. Keep it on if you want to. If you don't like it, turn it off. Okay, I would usually keep it on for reasons that I'd be happy to explain in office hours, but are unrelated to anything related to the test due on Friday. If I were to fit this polynomial model, this 4th order polynomial model, I again see this goofy looking fitted line drawn in. I don't love that. Cover that up, cover that up. But once we get down to our analysis of variance for the model, it looks the same like we saw earlier. Our effects test is the same. Well, is it? Maybe it's not. The effects test earlier said, is there a difference across the 4 treatment groups? Our effects test here is there an effect of tramping passes having control for the other 3 versions of tramping passes? Tramping passes squared, tramping passes cubed, and tramping passes to the 3rd, 4th power. That's sort of a goofy way of fixing things, but under estimates, if we go with sequential tests, then I think we've cleaned things up a little bit. Is there an effective tramping passes? Is it better than nothing? Yes. Is a curved model with tramping passes squared better than the linear model? Yes, it is. Is adding a cubic term better than adding than our quadratic model? It seems to be. And is tramping passes to the 4th power better than the model with just the cubic term? And the answer seems to be yes, it is. Okay. So the claim is we could fit this line, okay, and whether it's linear or quadratic or cubic, ultimately we say that it fits the same, and we're happy about that. The additional benefit, though, of that is if I have a quadratic or a cubic model, I can If the higher order terms are not statistically significant, I can get rid of them. I can get rid of them. Hmm. Getting rid of the higher order terms. If I found that tramping passes the fourth power was not statistically significant, I could remove it and have a model that's only cubic. And if I found that the tramping passes cubed was also not significant, I could get down to tramping passes squared. And if I have a fit that's comparable, that's quadratic, comparable to the 4 degree of freedom categorical fit, I'm going to use the fewer term model. I'm going to sort of say more degrees of freedom for error, reducing mean square error and increasing sums of squares for the model. I think one problem with this example is here, we haven't checked for our assumptions being valid, and if we were to do a transformation of the veg height, we'll do a little bit better. Let's look at that with Graph Builder. If I was showing you the veg height as a function of tramping passes, that looks very distinctly curved. If I were to scale this, okay, um, under axis settings, I might be able to use a linear. No. Let's use a logarithmic scale. Does that look far closer to linear now across my different levels? It seems like it's a little bit better. The only problem is, I guess, zero tramping passes can't be dealt with. But is this closer to linear? It seems pretty darn linear to me. It suggests that a transformation of your x variable is a good way to go, or perhaps a transformation of the y variable is a good way to go. I'm going to try building a new variable. And where do I do this? Where's my data? There are my data. Okay. I'm going to go with the log. Okay. And I go with log base 10 of tramping passes TP plus 1. Now, the reason I'm going to add the 1 is if I have 0 tramping passes, the natural log of that is undefined. But if I add 1 first, then we're absolutely fine. Oh, yeah, I need to, under column info, column properties, better yet, column properties. And let's go with the formula. Yeah, literally, okay. The log base 10 is transcendental. Log base 10 of what? Of the sum of two things. So I'm going to say 1 plus then the number of tramping passes. Okay, so if it was 0 tramping passes, then I add 1 to that and then take a log. Yeah, that's going to be 1. If I had a 75 and then add 1 to that, it'd be 76. The log base 10 of 76 is a little less than 10. The log base 10 of 201, because remember we added the 1 before we took the log. That's going to be a little bit over 2. Yeah, this checks out. Let's look at our graph of veg height plotted against our log base 10 of tramping passes plus 1. Is this pretty close to linear? My claim is yes, it is. So I'm going to want to maybe model this as a linear trend. And we're going to see if there's any departure from linearity in our trend. Okay. So our new x variable, which is quantitative, it's a version of our categorical treatment. It's literally the number of tramping passes plus 1, then the log base 10 of that. Let's go ahead and fit a model. So under fit model, the veg height will depend on, well, the log base 10 of tramping passes plus 1. And I'm going to go with, again, macros to the polynomial to degree of 4. So log base 10 of the tramping passes plus 1. That value squared, that value cubed, that value to the fourth. If I were to run that analysis, again, it's going to seem maybe a little bit wrong in some ways, but because I don't love the way, but at least they're always positive here. Our fitted model here still has an R squared of exactly what we had before. If we had our uh, five different, uh, five different level fit for ANOVA, 4 degrees of freedom, I still have 4 degrees of freedom. And the question is this, can we get rid of some of these complex terms? Our effects tests are, well, hard to work with because they're correlated x's. Like with the legs part data set, our p-values are elevated to be considerably higher than if we had done an appropriate sequential analysis. So under estimates, let's do them sequentially. And let's tackle the questions. Is a linear fit of log base 10 tramping passes plus 1, is it better than nothing? And the answer is heck yes, I love the linear fit. Is adding a quadratic term helping above and beyond linear? Nah. Is adding a cubic term better than quadratic? No. Is adding a quartic fourth order polynomial better than our cubic? No. I might very well say you don't even need the quadratic, the cubic, and the quartic terms. I might be able to do about as well with just one linear term. So I'm going to go ahead and fit that model just now. Recall. Oh, yeah, get rid of the higher order terms and delete all the higher order terms, leaving only just that one. I click run. And what we're spotting here is R squared. Instead of 89%, it's now only 86%. Bummer. But my sum of squared errors was like 30. Now it's 37, a little higher. What I was able to explain, 243, yeah, I'm able to explain only 236 now, right? But notice that my mean square for my model goes from 60 up to 236. And my mean square error, it was at 2.06. It remains really tiny. So mean square error isn't going down much. When you remove statistically unimportant terms, mean square error either stays about the same or it goes down, and mean square for the model climbs. Now, imagine you're in a situation where we could barely spot an effect of tramping passes in a linear trend model like this. Because of the large mean square and large F ratio, it's unlikely without enough data that you would spot that trend if you trail with this as categorical. The punchline here is sometimes we'll spot trends that you wouldn't otherwise be able to spot if you model them as trends. Again, this five level model, five categorical, I guess, five quantitative levels for my variable that we could treat categorically. Don't treat it categorically. Treat it as a linear, a quadratic, a cubic, and a quartic model. And indeed, we could peel off the higher order terms, those that are not necessarily explaining things, and you're going to be more likely to spot trends that really do matter. That seems to be about the biggest deal for what we need to know for today. So let's leave it at that and say the lab activity walks you through this idea in the context of a different data set, a more complex experiment where the goal is really there's like two different ways of treating. So that's a 2 by 2 experiment, and we're measuring at different points in time, and we're going to fit the time trend as categorical groups at 0, 30, 60, 90, and 120 minutes. Or we could fit that as a quartic model because 5 different levels, 0, 30, 60, 90, 120, 5 different levels. We could fit it as a quartic model, or maybe you'll be happy with cubic or even quadratic or maybe even linear, but my guess is you'll end up with quadratic. And peeling off those two higher order terms gives fewer degrees of freedom for the model, increasing mean square for the model, increasing your chance of seeing something that's really interesting in the data. So good place to stay. I'm going to pause for a moment, and if you got any questions, we'll include them in the recording. And if you don't, I'm going to stop the share. and then stop the recording.
Yeah, I think I'm okay.
Cool, cool.